Hello, my name is Sam Billand, and this is Lab 5, Falling Magnet in a Solenoid, for Physics 2212. In this experiment, we're going to collect data and prove Faraday's law and its relationship of time-varying magnetic fields, changing magnetic flux, with the produced Curry electric fields, induced current. And this is done by dropping a bar magnet through a roll of aluminum foil, a non-ferrous metal. And then eventually we'll create a computational model using the collected dimensions of the foil tube and the conductive properties of the tube to create a visualization of the experiment. Before the final experiment, initial observations were made about the bar magnet, the non-ferrous tube, and their interactions. First, the dimensions of the tube were measured, these being the radius of the foil rings and the tube's length. Next, when dropping the bar magnet through the tube, it significantly slowed down. So this must mean there is an opposing magnetic force. Therefore, the aluminum tube uses Faraday's law to create an induced current and an opposing magnetic field on the magnetic field of the bar magnet. The two main equations used in this lab are Faraday's law of induction and Ohm's law, shown on the slide. Assumptions in the lab include that the number of loops is equal to the number of rings analyzed on the aluminum tube, the voltage used in Ohm's law for induced current is the induced EMF from Faraday's law, and the flowing current in the rings of the tube create magnetic field opposing that of the bar magnet. Here's an in-depth look at the computational model's code. First, he started by recording the dimensions of the foil tube. Then, the bar magnet's visual was created, along with a function that computes its magnetic field at a distance r from the magnet. Furthermore, the change in flux of the falling bar magnet through one ring of the aluminum tube was calculated. Looking further down in the code, the force of gravity on the falling bar magnet was calculated, along with the current flowing through the ring of the tube using Ohm's law. Furthermore, the sum of the forces from the ring on the magnet for each ring as the magnet falls through the tube were calculated. Finally, the net force on the bar magnet at times as it falls through the tube was found, and diagnostics on its velocity and position were taken. At the end, the velocity versus time graph was plotted, and a print statement on the amount of time it takes the magnet to fall through the tube was created. On this slide, you'll see two side-by-side images as the bar magnet falls through the aluminum tube. The red highlighted area represents the induced current in the aluminum tube. On the right, you'll see the velocity versus time plot and see that while in the tube, the velocity remains constant and the bar magnet remains in the tube for 1.96 seconds. When comparing the experimental time for the magnet to fall through the tube and the computational model time, they are almost the same, being 2.1 seconds and 1.96 seconds. To make the model time more accurate, you can analyze the falling magnet at more points along the tube, thus accounting for the opposing magnetic field of more rings. Furthermore, when asked which color corresponds to clockwise current and counterclockwise current when the magnet falls through the tube, it is easy to tell. As the magnet falls through the tube, it turns red. Faraday's law of induced currents flows opposite the increasing changing flux, which is directed downward. So, the induced current flows counterclockwise, meaning that red stands for counterclockwise current and blue stands for clockwise current. What would happen if the resistivity of the conductor were reduced to almost zero? Well, with no resistance in the tube, the current would accumulate in the tube as the magnet falls, and produce a magnetic field that would be equal to that of the falling magnet. Therefore, the bar magnet would remain suspended in the air within the tube. Furthermore, what if holes or slots were cut into the tube? How would this affect the current flowing through the model? Well, with a hole in the tube, there would be a larger area, meaning that there would be a larger flux flowing through each ring when the magnet falls through. This means there is a larger induced EMF due to Faraday's law, so more current flows through each ring in the model. Therefore, by creating the falling magnet through a non-ferrous tube model, we proved, calculated, and discovered that there is an induced current through the rings in the tube. This current then creates an opposing magnetic field and force that acts on the magnet, slowing it down slower than if it were dropped in free space.